Okay, well, thank you very much for inviting me to this. I had hoped to be able to be there in person, but unfortunately, circumstances meant that wasn't possible. So thank you for allowing me to give this presentation by Zoom from the other side of the planet and the other side of the day. So as I said, I'm going to be talking about automata chemistry experiments with replicators and parasites, and I will try and link it in with the idea of guided systems towards the end, guided self-organizing systems. But I'll start off talking about automata chemistries. And I'm going to be talking about some experiments that we've done with our string mol automata chemistry. I'm going to be talking about 3 different sets of experiments with that. First, I'll give a little introduction to what string mol actually is. So an automata chemistry is one where the artificial chemistry molecules are themselves little computer programs, usually written in some kind of assembly language. And here it's a hand-designed assembly language for our experiments. And this assembly language for string mol has got only 7 what we call functional opcodes, which can do very minimal things such as manipulating pointers, copying other opcodes, and cleaving strings that are being built and so on. What makes us able to do evolutionary experiments with this is that there is a small probability of mutation whenever the copy opcode executes. And it's purely that small probability of mutation that allows these strings to evolve. We also have 26 non-functional opcodes, letters of the alphabet, which we use mostly to form binding sites on the particular string. And the point about string mol, as opposed to many other automata chemistries, is that the execution occurs when 2 strings bind. So it's not just an autonomous execution of a single string, but when 2 strings bind, one string executes its code using the other string as data, or at least that's what happens to start with before a lot of evolution has happened. And we have a Smith-Waterman-like complementary binding, so that the 2 strings can bind in a pair with complementary on the alphabetic characters, with a kind of a ROT13 complementarity in the alphabetic symbols. And because it binds on a region rather than a single character, we can have a soft probabilistic binding. If there's a slight mismatch in the characters, then there's a lower probability of binding. And so the strings can also evolve how the probability of binding with each other, as well as evolve what they execute. We also provide a small chance of decay for every string. So in other words, these strings, in order to survive, they need to replicate, and that's the evolutionary pressure on the system. So just thinking of that, we have a load of strings, they bind to each other and they execute, and that's mostly what happens. So here's how we start the system. We've hand designed what we call a replicase. This particular string, you don't need to understand what's going on, but this particular string, when it binds to a copy of itself and executes, it produces a 3rd copy of the string. And it does this within 65 instructions in the string. It takes 240 time steps to execute. And so you start off with 2 of these strings bound to one another, and at the end of execution, you've got 3 strings. One of the strings has copied the other to produce a 3rd copy. And this is hand designed to do this, and we call it a replicase. It's complementary alignments, as I said. So the string binding positions are in this area, and there's also some other complementary ones here for flow control. And then there's a little bit of junk here to allow a little bit of neutral evolution as well. And so we start with a bucket, a well-mixed bucket of 400 copies of this replicator, and just watch what happens. And so when we watch what happens, we discover that the string mol evolves a wide range of emergent behaviors. The simplest of these maybe is a sweep. A mutant species takes over the bucket. So we start off with 400 of the hand designed strings, and after a while we've got a load of different strings in the bucket. Hypercycles evolve quite frequently, and a hypercycle is where string A copies a different string, string B, and B copies A. So there's some mutualism, A copies B, B copies A. But because of the way the strings have evolved, neither species can actually bind to a copy of itself, so it can't copy itself. So A requires B and B requires A in order to survive. And in fact, some runs have multi-species hypercycles with more than 2 of these interdependent species. The only mutation built into the system is a micromutation on copy, but some macro mutations emerge from this, where the way the string acts is it chops off large sections of strings or glues large sections of strings into the system. But the thing I want to talk about today mostly is the evolution of parasites. So a parasite is a species, a kind of string that can be copied, but itself does not copy any other species. And the parasites are typically much shorter strings, and so they're copied faster. And so they have an evolutionary advantage because of that. And one of the things that can happen if you get parasites is you can get a death spike. The parasites take over the bucket, and once the bucket is full of parasites, well, there's nobody left to do any copying. And so then you can copy the parasites and the parasites die out. So here's a little picture of a time series. So this is several million time steps along this axis. And this axis is the number of the strings of a particular species, and the different colors represent different species. And so you can see here, to start with, we have our seed species, but then we have a sweep of a new mutant that takes over, and then after a while another mutant takes over, and so on and so on. We can have slow sweeps where that takeover isn't very sudden. We can have here a region of mutualism where we have multi-species hypercycles. We can have coexisting subpopulations that aren't actually hypercycles, but they are just living together happily in the bucket. And then typically what happens after a while, you maybe get some more of these sweeps, but then at the end you get this death spike. So this species here is the parasite, it takes over the bucket, everybody else dies out, and then it goes, oops, there's nobody to copy me, and it dies out. And that's a very typical behavior of the bucket of string moleskins. So what we wanted to do was to investigate these parasites and possible defenses against parasites. And it's been discovered that some simple simulations of parasitism, that if you have a spatial component, then you can survive for longer and build defenses against the parasite. So that's what we did next, was to have spatial string mole rather than a bucket of string moles. Parasites always emerge, and in the bucket, there's always a death spike. We haven't managed to make a bucket of these strings that doesn't have a death spike so far. But in the spatial environment, the idea is that the parasites are located in a relatively small region of space. And so the death spike itself that you might end up with is also localized, but other strings can survive in other parts of the bucket. So our question here was, if we do this, can the system as a whole survive? And here's a picture of a run in this spatial environment. Near the beginning of the run, this one here, the color, by the way, the color bar is the length of the string, which gives you an indication of the species changing. So short strings are dark blue, intermediate strings are sort of pale color, and then very long strings are this dark red. So you start off with the hand designed string, which is relatively long, but you can see around the edges of this space, there's sort of a blue border of very short strings, and these are the parasites. And then after a while, the strings, the replicator strings, still are replicating, but they've got shorter. and they're still surrounded by parasites. And as time goes on, there's evolution, and the parasites are always there and always around the edges, but the bits in the center are managing to survive. Different length strings evolve. In this particular run, after a while, in fact, the strings, the replicators managed to kill off all the parasites, and the whole arena is full of replicators. But then after a while, the parasites come back and things continue. And in this particular scheme, we've managed to do quite long runs and not have a death spike. The system manages to survive. Not all runs survive, but we've had several runs that do survive. So there's quite a lot of complexity in this system. And this is a chart of, again, it's time along here, and then it's number of strings of the species here. And this is just a stacked plot. So you can see at sometimes you get quite a large number of one particular species, and then quite a lot of other species. But at other times you get a high number of particular, a lot of different species, each with a small copy number. And this region here is the region that I pointed out where the parasites have been killed off and everybody was happily replicating and evolving away, and then the parasites come back a bit later on. So you get a very complex behavior over time, much more complex than the behaviors that we saw in the bucket, where we only ever had one or two different species, mostly at a time. So how are these managing to survive? So here's a little example of what happens, first of all, with the first parasite. The way to look at this is the string that is the replicator. And if it binds to a copy of itself, another replicator, and so the binding region is this red box, they bind here, and then the instruction pointer along the top just moves along until it gets to the actual code region, which by this stage is this pink area here. And this is a copy loop, and this pointer goes round and round the loop, and it's copying this other string until it gets to the end of the copy loop, when it gets to the end of this string, and then it goes along and then terminates. And so you start off with 2 replicators, and after, in this particular case, 230 steps, you end up with 3 replicators. However, if this replicator binds to this parasite, and this parasite has evolved, it's essentially the same as the replicator, but it doesn't have the active code area, so it's shorter than the replicator. It binds to this, the replicator moves along, gets to this copy, copies the parasite until it gets to the end of the parasite, and then terminates. And because the parasite is shorter, this copy loop doesn't have to go around so many times, and so it copies it more quickly. It only takes 188 time steps to copy. You start off with a replicator and a parasite, and you end up with a replicator and 2 parasites. So that's the evolution of the first parasite. And so then what happens? Well, the replicators evolve a defense against the parasite. So here we've got 2 copies of a new replicator. Notice it's quite a bit shorter than the previous one. And the binding region is actually now at the beginning in both cases. And it's got a much more complicated execution now. It moves along this initial, when it binds to this replicator, it moves along until it gets to this blue area. And what the blue area does is simply it's a small piece of code that flips the execution pointer to the beginning of the other string. And then it moves along this other string until it gets to the same blue area, which of course now flips the pointer now back to where it was before. It moves along, gets to the copy code, copies the first string, and then terminates. And so now after 262 time steps, you've ended up with a new copy of the replicator. But this is a defense against the parasite, because when the replicator binds to a parasite, it goes along, it flips the pointer onto the parasite, but the parasite doesn't have this little blue code, so the pointer never gets flipped back, and no copying occurs, and you end up with what you started with once the execution is terminated, 218 time steps. So not only is the defense against the parasite, and it doesn't copy the parasite, it also binds to the parasite and keeps the parasite from doing anything nasty anywhere else for 218 time steps as well. But of course, evolution continues, and the parasite evolves a defense against this defense, and then the replicator evolves a defense against the defensive parasite, and so on and so on. And after a while, you get something that looks like this. You've got counter defenses and counter defenses, and I'm not even going to try and talk through what happens here. It is just amazingly complicated. Things are bopping about all over the place. But in this particular case, this replicator can copy this one, 224 time steps, and in this particular case, this replicator does not copy this parasite, so it has a defense against this parasite. And as time goes by, things get mostly more and more complex. So what we have here is the way these parasites actually evolve is essentially they evolve by removing the code that allows them to replicate. And that makes them smaller because it's removed some code, and therefore they can be copied faster. So as I said, that gives you an evolutionary advantage. And the replicators evolve many defenses against these parasites, particularly check code, that the partner is similar to self, so that you're copying someone like yourself rather than copying a parasite. Now remember, the only evolution is a small mutation on a single opcode when it's copied. And so this is quite complex behavior that's been managed to evolve an opcode at a time. But then once the replicator has evolved a defense, the parasite then re-evolves from this new replicator. It keeps the check code and simply ditches the replication code. And so it gets shorter, it has an evolutionary advantage, but then more checks evolve and so on. So interestingly, with this form of evolution, we don't see two parallel strands of evolution of replicators evolving from replicators and parasites from parasites, which you do tend to see more in natural parasites. But in this particular case, we only see one evolutionary strand of replicators, with the parasites themselves continually evolving from the more and more evolved replicators. So, as I said, it gets quite complicated, and we quite happily talk about replicators and parasites, but it's a bit difficult to classify these once the reactions get more complex. So we started off with the definition of a replicator is it simply is something that copies other strings. But as we can see, as we've seen in some of these examples, its behavior depends on the other string. It may replicate some strings, but not others. For example, it may replicate its copy of itself, but not a parasite if it's evolved a defense against that parasite. And once the execution pointer is bopping about between the two strings quite a lot, which string is actually doing the copying and which is being copied, given the complexity of the interaction, is quite difficult to determine. And in fact, we've seen cases where a string will copy the string it's bound to, but destroys itself in the process, and so on. So it's actually quite complicated. And the parasitism is also equally complicated to define. You start off by saying a parasite is one that does not copy other strings. This is even harder, in fact, because this is a counterfactual property. It's unobservable in the running experiment. You can't observe a parasite not copying another string, because the whole point is that it's not doing that. And again, just like with the replicators, the behavior of a parasite depends on the other string. It may replicate some, but not others. After all, a replicator with defenses does not copy parasites. Does that make it a parasite? Well, no. And a parasite might replicate itself, but not the other string, and so on. We've seen all these different behaviors, and so it's quite complicated. So what we eventually had to do was give some formal definitions of what we meant by replicator and parasite in a reaction. So it's not a property of a specific string being a replicator or being a parasite. It's a property of either a reaction or even a whole reaction network, but this is a replication network, or this is a parasitic network reaction. We gave formal definitions of what we observed happening. So we had to have formal specifications of parasitism, of hypercycles. There were a bunch of other things that we noticed happening as well. And actually formulating these definitions was key to the analysis that we were doing. We used those definitions to implement the analysis tools and to track how these pairwise interactions were affecting parasitism and affecting other properties of the system. The last thing we wanted to do was have to manually step through each reaction and figure out what was going on, although we did have to step through some reactions in order to figure out what was going on, in order to specify it and then build the tools. So here's a little picture of some of the analyses that we did. Again, it's time along here and numbers of strings up here. This is the same data, but plotted in two different ways. What we're plotting here is the length of the strings. Now, of strings, so it's actually, we're plotting the distribution of lengths of strings. And at the top one here, this is the median length, is the dark line, and then we've got various quartiles and percentiles to show the range. So we can see, for example, at this point, that the string length is gradually decreasing. Now remember, this again is the area that I said was where the parasites had died out. That's why everything's quite narrow, really. We've mostly just got replicators, but those replicators are evolving to be slightly smaller because, again, that makes them be able to replicate faster, and so they have an evolutionary advantage. But actually, the structure in the arena is a bit more complex than can be shown just by having a median and quartiles. So this is a heat plot of the different lengths, and you can see here there's a main set of strings of a particular length, but there are other ones, and they form these bands, and these bands are sometimes big sections of string that gets added on once, on twice, on three times. Which isn't really doing anything, but is there in the string. And then we can visualize other kinds of properties of the systems. This is two different runs being shown here, and where we've classified the reaction types, where the red reactions are non-replication but non-parasitic reactions. The green one here is hypercycles. The orange one is self-replication, and the blue is parasitism. And so you can see here that in some cases, when you get hypercycles, you don't get self-replication. It tends to be one or the other. It's not always exactly one or the other, but each seems to be a different defense against parasites. So what we can learn from seeing this is that even this simple string model exhibits quite complex behaviors, including hypercycles. But in order to stop these death spikes, you do need to have space. Space allows parasites in one area to die out, but parasites in the other area to have defenses evolved against them. But it seems to be this parasitism that's the driver of the increasing complexity of the various strings and their behaviors. Although with parasites, you might think they're much shorter and they can be copied faster, that gives them some evolutionary advantage. But the longer strings of the replicators can include more complex defenses against the parasites. You need space in the string to build those various defensive regions. And so the longer strings of the replicators and the more complex defenses win out in the end. But in that region where I showed you where the parasites went extinct for a while, the defenses were very good, the complexity decreases. It evolved, actually the strings evolve out their defenses. They don't need them anymore, so they can evolve them out to become shorter. They're still replicators, but they're shorter, so they can evolve faster, so they're having evolutionary advantage, but now they haven't got the defenses, the parasites emerge again, and the complexity increases again. And so it really is the parasitism that seems to be driving the increase in complexity here. So we also learned some lessons in analysing this quite complex system. In particular, the summary statistics don't seem to be particularly helpful because they miss the important details, they miss the fine structure, they miss the outliers and so on. Also, the generic measures that are often available in the literature for these kinds of systems are not always applicable because they often make specific assumptions about the system that might not be true, particularly in a highly evolved system. And so you really need measures that are specific to your own kind of system. And the analysis tool development, weren't able to develop the tools up front. We had to develop them following an experimental approach. We observed what was happening. We hypothesized that particular mechanisms were happening. We developed the tools to measure those mechanisms and test the hypotheses and so on. And also, behavioral measures are much more important than structural measures. Very often in the literature, the particular measures that you find for complexity and so on are structural, but in all of these systems, it's the behavioral measures that are of most interest because it's things like the behavior of parasitism or the behavior of defenses against parasitism that are the key behaviors and the key drivers of the complexity. And again, the behaviors are very system specific, and so they're much more difficult to find generic measures for them. So that was the experiments that we did with what we call straightforward string mol, looking at parasites. And I'm now going to also talk about another set of experiments we did with string mol on the universal constructor architecture. So you probably know about von Neumann's universal constructor architecture that he developed via his cellular automata approach to when he was investigating how various systems might be able to self-replicate. And the idea here is quite obvious now, but was brilliant when it was invented, is that you've got two parts. You've got a kind of data or code part, which is analogous to the genome. And in this, you've got various little, what might be called modules of code that can do various things. And then you've got the active machines, which are the expressed code actually executing. And so the copier code is expressed as a copier machine, which copies the genome. The expressor code is expressed as an expressor machine, which expresses the code. So that it's like the compiler that goes from the code to the executing machine. Then in the von Neumann architecture, there was a controller which controlled when copying and expressing happened. And then you could have an application or payload, which is something that that you have there for the system to actually do something rather than just copy itself. And the analog here is that the static part is the genome and the active part is the proteins. And there have been experiments in the past where people have set one of these systems up in an artificial chemistry and tried to let it evolve and found that you can't evolve this part of the system because it's too fragile and you can only evolve this part of the system. So we tried to look at this in string mol. we started off with a naive implementation where the proteins are simple string mole machines, they're little string mole programs. And then the genome is simply the string, the concatenation of these relevant machines. So expression is trivial because it's just there directly. But there's a problem. There's no way in this system to distinguish between the static genome and the active proteins because essentially they are the same thing. It's a bit like an RNA world system here. Copiers bind too much. There's no way to constrain them to copy only the DNA, only the genome. They copy the proteins as well. And because they're copying the proteins as well, there's no need for the genome, and the original structure just evolves away, just leaving the protein machines. So that's not terribly exciting. So we thought about this a bit more and decided, well, we're talking about genomes and DNA, let's actually take this a bit further. And so we built a non-trivial encoding of these protein machines, these string mole machines, into a genome, so that this genome now really is data, or is the uncompiled code, and we call it G for genome and 0 for the first iteration of it, 0, because we're computer scientists and we start counting at 0. Then the expressor is a string mole machine that can actually execute, and what it does is it binds to the genome, and as it executes along the genome, it translates triplets in the genome into whatever those triplets are encoding for. So you can see this is quite long. This is 3,500 opcodes. And there's a ... because this isn't all of it, but this is the entire expressor here. So it's a much smaller thing, very much like the difference between DNA and proteins. And then the copier machine is designed to copy only the genome and not the proteins. We can now, because we've got sufficient difference in the structure of these two systems, we can now make the copier copy only the genome and not the proteins. And in this particular case, this structure now, the von Neumann architecture, constructor architecture, is maintained while the system evolves. So I just want to quickly talk through a few of the evolutionary processes that we saw. But first, here's what the normal operation of the copier, which I'm putting here just to show you what the how the diagrams work. It's a bit like a Petri net. This bar here represents the place where the binding and execution occurs. So the idea is here is we have a copier, C0, and a genome, G0. The copier and the genome bind at this bar, and the copier executes by copying the genome. And so at the end, when everything's finished, the copier and the genome stop binding, and the copier goes back to being itself, the genome goes back to being itself, and the copy of the genome now comes out of the system. So we start off with a copier and a genome, and we end up with a copier, a genome, and another genome. And that's the way the copier works. Similarly, the expressor works in a similar way. An expressor binds to a genome, and it expresses the genome. In other words, what it does is it expresses the copier, it expresses the expressor, and it expresses the payload. In this particular architecture, that's all we've got. We've only got the genome simply encodes a copier, an expressor, and a payload on application. And so that's how the expressor works. So first experiment results, sorry, it's quite a busy diagram, but there's quite a lot going on here. The copier and the genome bind, and the copier copies the genome, but it makes an error on copy, and that's what this red line here says. And so what it does is that the copier copies genome 0, but it makes an error and it produces genome 1. And then when the expressor binds to genome 1, it expresses the same copier, but expresses a mutated expressor, because it's expressing from a different genome, a mutated genome. And then when that mutated expressor goes back to the original genome, it then produces a different copier and yet another expressor. And that new expressor goes to the mutated genome and expresses a third expressor. And then finally, we get to a stable state where we've got expressor 3 and genome 1. So the mutated genome and the expressor, and we get a stable state of copier 1, expressor 3, and so on. So in this case, all of these systems have changed. So we started off with this copier, but very quickly became that copier. We started off with this expressor. We had an intermediate expressor, and we ended up with the gold expressor. And we started off with a black genome, but we ended up with a pink genome. So everything has mutated. In fact, the only thing that hasn't mutated in this particular case is the payload. So we end up with a system with a mutated genome that supports a mutated expressor and copier. So we have managed to evolve and mutate the expressor and copier code in the genome. Then we get something quite interesting happening. This is a different experiment. Again, we get the copier and the genome. The copier copies the genome, now makes an error on copy. This is a different error. So we've got a new genome. The expressor on this new genome gives a different expressor. This different expressor on the original genome gives yet another expressor, and that is then stable. So what we end up here with is the same copier, the same genome. We did need a different mutated genome in the middle, but essentially towards the end. But what we've done is move from expressor 0 to expressor 2. So we've got the same genome, but now it's expressing a different expressor. And this one has actually also managed to mutate the payload, but that's not particularly important here. The idea is we've got semantic takeover of the expressor without an eventual change of the genome. We can have a similar semantic takeover of both expressor and copier. I won't go through the details here, but again, what you see is that you have an error on copy of the genome, which means that you end up with a different copier and a different expressor, even though eventually you have the same genome. So that shows that this can happen in multiple ways. It wasn't just an accident, but we saw it in one way. And then finally here, we have a semantic change in the system without even miscopying the genome. So what happens here is the expressor, when expressing the genome, the expression has an error. And so it expresses a mutated expressor. And that mutated expressor and the original genome gives a secondly mutated expressor, and that secondly mutated one is now stable. And so with no error in copying the genome at all, we have changed the expressor from E0 to E2. The only error there is on expression and not on copying the genome. So there's quite complex evolutionary activity happening here. So I just want to say about this particular example, the string model implementation of this von Neumann architecture also exhibits complex evolutionary behaviors. It's not now looking at parasites, it's now looking at semantic changes to what's encoded in the genome. So errors on copying can change the genome as you would expect and change what it expresses. And you can even see those changes back in the original genome. But interestingly, errors on expression alone can result in fixed changes of expression. So expressor 0 expresses E0, but E2 expresses E2. So which E is actually encoded on the genome, because it's the same genome, it's just a different expressor. So the meaning of the genome is not absolute. The meaning of the genome is relative to the environment in which it finds itself. Okay, so this string model system can exhibit many lifelike properties. I put that in quotes, but I mean, it can evolve, it can evolve the von Neumann architecture, it can show parasites, hypercycles, and so on, and it can show semantic change in the genome. And so what we want to do in future work is to explore open-ended behaviors in this kind of evolution. And that's just where I want to conclude on trying to link it back to the topic of this conference about guiding systems. So we can think of ordinary evolutionary algorithms, goal-driven systems, as guided exploitation. You've got an explicit fitness function, you're optimizing, and you're guiding the system to that optimum. Stringmol, by contrast, is unguided. We've got no fitness function except in intrinsic survival, but it's exploration. We're not trying to find some extrinsic objective. And the aspatial gives you emergent reaction types, and the spatial gives much richer complexity. The novelty search algorithm that you by Lehman and Stanley is a kind of a guided exploration of a feature space. So it's a dispersive algorithm. Your fitness function is to be different from everybody else. In some sense, it's trying to maximize the variance in the population without needing a population of populations to do that. And so that's quite interesting. But it's maximizing variance within a given feature space. If you want truly open-ended systems and truly open-ended evolution, you want not just variation where you've just got variations on the theme. You want innovation where you get new kinds of things, and transformations where you get new kinds of things as well. So there, you might want some kind of guided exploration of a changing, growing, evolving feature space. And that's the kind of area that we're interested in looking at in some of our future work. So I'd just like to conclude there. I've got some further reading that you can look at if you are interested in that. So thank you very much.
I've got time for questions. Yeah, why don't you come down here? This general area should be fine.
Hello, Susan. Peter Wills here. Very glad to see you again, and thank you for a nice talk. I just wanted to explore with you the idea of trying to evolve a system in which the complexity of expression and obviously the complexity of the genome could increase with time. It's the sort of thing that I've tried to do with John McCaskill before with the GRT systems, gene replicase coding systems. And we sort of got so far, and now I think that with this architecture that you're using, I mean, I like very much the fact that you've turned it right over to the von Neumann architecture rather than just using a simple Gillespie kind of algorithm and very simple string processing. I mean, this is really good, and it's very different from the lambda calculus, which was sort of first used to do anything like this. But the way in which biology must have evolved was to have had a very simple code, a very simple expressor to start off with, from which it could become more complex. And of course, your relativity of the meaning of the genome in terms of the expressor that you have lends itself exactly to that, because it hits the nail right on the head. That's the whole point about expression. It is completely relative to its circumstance and what it itself does. But there's got to be some way in which it can open up and become more complex. And in that sense, you have to build some more chemistry, a greater realism of chemistry. And I just wonder what your thoughts are on all of that. Sorry, I shouldn't have just raised on.
Yeah, Yeah, that's really, really interesting. I mean, part of this at the moment actually is it's in two halves. The evolution of the more complexity is in the very simple string model system, which was kind of originally built as almost a model of RNA world. And then the evolution of the semantics and the expressors is in the DNA model. And we haven't seen the parasites and so on in that. Mostly because it's a much bigger system and so runs much slower, and so we haven't run such long experiments with it. But your point about more complex chemistry, I think one of the real issues is trying to. We have this thing: make everything soft. Try and because you need to evolve not just you know, the strings. You almost need to be able to evolve the opcodes and things as well of what it can do. Yes. And that's something that again we've looked at in a sense. I did have a PhD student who I said was his job was to evolve the least efficient copy operator that was possible, because he broke it down into lots of separate bits so that different parts of even this what looks like an atomic operator could be evolved separately. But yes, it's very complicated. I think the thing that we found with the string mole was this actually the soft binding, being able to evolve the binding strength so that molecules that started off being able to bind to each other eventually couldn't, or that they could evolve to bind more strongly, was also very important. So we came up with a bunch of design principles, one of which was everything soft, or everything as much as possible soft. In other words, put as much as possible into what can evolve, into the biology rather than into the physics. But this kind of intermediate level of what's the actual chemistry is very interesting. So what we want to do is to have a rich enough system without just simply being a simulation of natural chemistry. But yes, that's hard.
Yeah.
That was a very long answer to your question.
My long question.
Yeah, which was basically, yes, it's. I agree with you, but it's hard.
Yes, thank you.
Hi, Susan. Thank you for your talk. I was wondering what similarities from your studies of parasitism could be generalized or extrapolated or compared with predators that basically you have a stressor and then that can or may not promote complexity, or also within the same group, just having some sort of competition, like this idea of Machiavellian intelligence that kind of, as Dunbar suggests, promoted the evolution of intelligence in hominids. I don't know whether from your experiments you could comment on that.
That's an interesting question. We hadn't thought about it in that kind of way. I think the idea with the parasites was it's a relatively simple system where you've got a freeloader, where the system's trying to do something, which is survive, and then there's a freeloader coming on. So I suppose you could think of it in some kind of game theoretic terms of the freeloaders coming in and the cheaters coming in and so on. We haven't looked at it that way in that detail, because what we were trying to do was allow the defense mechanisms to evolve, because very often these kinds of systems put in quite a crisp, the behavior is that it cheats, but it can only cheat in one way, and so there's really no way that you can then evolve a defense and then evolve a defense against that defense and so on. So we were really focusing on the how does it stop the cheaters, and spatially one of the ways is by protecting itself by having a smaller boundary, but the other way is actually by evolving these kind of different behaviors. So I imagine that it is going to be part of the way some of these other approaches work. The main thing at the moment that we think is a bit different from the way real parasites work is because of the lineages, that the parasites all evolve from the replicators. They don't evolve from other parasites, which is obviously not the way when you've got a predator prey. You know, you don't have all the predators evolving from the prey each time or something. So there's clearly something else that's needed. We're not quite sure what that is yet, but yeah, I think all these things are linked together. Yeah.
Yep.
Yeah. Thanks. I'll think about that. Yeah.
Just a final comment. In many species, it's observed that you end up with evolution of prudent parasites or prudent predators precisely so that they don't become extinct. So they kind of develop their own self-regulation mechanism so that they don't wipe their hosts.
Yeah.
Yep.
Yeah. Yeah. Thank you.
Yes, sorry.
There's a question in the questions that I can see. Mention that if copying created errors, it could alter the DNA up to find what these errors occur. In all cases, it's simply a mutation on copy. So when you copy one opcode, occasionally it copies the wrong opcode. Occasionally it inserts a copy, an extra copy, and occasionally it just doesn't copy it at all. And those are the main errors. And most of those errors are kind of fatal. But every now and again, you have an error that is sufficiently okay to allow it to continue to act, but just do something a bit different. Again, it's incredibly difficult to analyze these things because you've got millions of time steps and thousands of opcodes going on. I don't know if that answers the question, but yes, some of the analysis tools were trying to look at the different patterns of things that were happening, and but it's quite difficult because one, you're looking at a particular assembly language that we invented for the purpose of doing these experiments. So it's not kind of a well-known assembly language. It's the one that we're using. So it is a bit difficult to understand what's going on in some cases.
Okay, thank you. Mikhail?
Yeah, hi, Susan. Thank you for your talk, and thank you for your flexibility to begin with to give the talk live rather than over video. It's a question about evolution of evolvability. And I know you obviously published in this area, and you talked a little bit today about the self-referential nature, that mechanisms for defense evolve in response to parasites emerging and the process continuing. The question I have is slightly more specific, but in this context. I understand that replicators evolve mechanisms to discriminate copies of themselves from the parasites. And this sort of behavioral response is quite interesting, because the distinction between self and non-self is one of the key mechanisms that even autoimmune systems develop in response to different threats. And even in cybersecurity context, that's one of the areas where people focus attention, because one of the ways to attack a system is to attack the part which discriminates self from non-self. And so I'm curious whether you, in your simulations, identified some specific binding regions or something where the parasites exploit that particular vulnerability, the code which distinguishes self from non-self.
Yeah, there are at least two different ways of the self non-self. There are some where the system does actually check and goes along the whole string and copies itself onto the other string and then copies the other string. And there are other ones where it's a much coarser, it is simply a consequence of the behavior that it is itself. So the one about where it flips the pointer to the other string, and then only if the other string has got the pointer flip bit of code will it come back. That's a very coarse definition of self, of I count you as being self if you've got this pointer flip bit of code, but you could have lots of different code everywhere else, with the hope that the parasite doesn't have that. And that very coarse that very coarse definition of self is much more efficient, because it doesn't have to do so much checking, but also it can make mistakes that a parasite manages to catch that little bit of code, but not the rest of it. So interestingly, there's a trade-off, I think, between how much you want to make sure that the other one is you before you copy it, and how expensive that check is. I don't think that's quite an answer to your question, but the answer is really there are lots of different ways of defining what you mean by self, I think, and how faithful that check is, and that yeah.
Yeah, thank you, Susan. Thank you.
Okay, one more question from Daniel.
Hi, Susan. Thank you for a great talk. I have a question. I mean, one of the things that struck me in this type of models is that in game, when you do, game theory, rock, scissors, paper, whatever, you can actually evolve the complexity of your strategy, and it becomes more and more complex as you try to hide information or what you're going to do from the other player. Now, the interesting part is when you do it long enough, essentially it evolves towards perfect randomness, which is of course maximally complex in terms, but in one way it's actually maximally simple either. So of course, in this type of scenario, you have an idealized setup. But my question to you is, could you imagine a simplified version of your evolutionary model where essentially the structure of the chemistry is simply a spatial interaction pattern of players, and where you could actually do proper analysis how the complexity goes and how to make sure that it keeps actually not getting more complex and not just collapsing into simplified randomness?
So I'm not sure I've exactly understood the question, but the paper that we wrote about spatial string mole we did in collaboration with Pauline Hoekveg, who'd got starting from her spatial model, but where the actual evolution of the system was not intrinsic to the system. And then you can do lots of nice mathematical analysis of it because everything's under control. What we wanted to do with the string mole was to make the evolution intrinsic to the system, and so that the system could evolve its own behaviors without us trying to guide it or constrain it or anything like that, to see whether to see whether her results of space stopping the parasites taking over and our results of the intrinsic evolution of the parasites could come together. And that was the reason we were doing it that way. And frankly, I don't see any way of actually getting that kind of complexity evolution without that kind of letting go of your constraints on the actual behavior of what's going on. The whole point is it's going to evolve unexpected behaviors. And in fact, from our point of view, that's exactly what we want it to do. We want it to be open-ended and doing stuff that we had never even thought that it would do. So I think that, yes, you could do what you're wanting, but it's not what we're wanting to do, if you see what I mean.
Okay, thank you.
Okay, thanks.
Thank you very much for a fantastic talk, Susan. Thank you.